A retriever's job is pretty easy to state. All it needs to do is find documents in the knowledge base that can help an LLM respond to a prompt. If you think about it though, that's a pretty difficult job. Users aren't submitting well-structured SQL queries to your RAG system. They're chatting with your LLM the way they talk to another person. Meanwhile, the documents in your knowledge base might be anything from personal emails to internal company memos or articles from a medical journal. They might be rich in information, but it's usually structured for humans to read, not for a computer to search through it. Somehow, a retriever has to handle all of this messily structured information and rapidly return the most relevant pieces, all in fractions of a second. In this module, you'll learn about the primary techniques a retriever uses to accomplish this feat. You'll build a theoretical understanding of how each technique works, explore their relative strengths and weaknesses, and see how a retriever uses them in combination to provide the best possible results. You'll also be introduced to some strategies for evaluating a retriever's performance, and as always, you'll find some hands-on coding exercises and a programming assignment where you can directly apply what you've learned. I think you'll enjoy this deep dive on information retrieval. So join me in the next video and let's get started. Metadata filtering is the most straightforward and likely the most familiar technique used inside of a retriever. Let's have a look at how it's used and what particular benefits it brings to how the retriever works. Metadata filtering uses rigid criteria to narrow down the documents returned by a retriever based on the document's metadata. This metadata might be information like a document's title, author, creation date, access privileges, and so forth. Here's a simple example of how it works. Suppose you work at a newspaper and want to build a retriever for articles written over the history of your paper. The knowledge base would contain thousands of different articles. Each article is tagged with multiple pieces of metadata, including its title, the date the article was published, the author of the article, which section of the newspaper the article appeared in, and so forth. While the full text of each article lives somewhere in the knowledge base, the system can only search for articles based on this metadata. Querying this kind of index looks a lot like writing a SQL query. If you only filtered based on one piece of metadata, you could find every article published on a given day, or even every article written by a particular author. You could also write more complex queries and filter on multiple pieces of metadata. For example, you could find all of the articles written for the opinion section between June and July of 2024 by your favorite journalist. Only articles that meet every condition would be returned, and the rest of the articles would be filtered out. If you've ever filtered a table in a spreadsheet, you've already done metadata filtering. You're just using a strict set of criteria to determine which members of a larger collection of data you want to use. Inside of a typical RAG system, you won't use metadata filtering to perform retrieval, but rather to help narrow down results returned by other retrieval techniques. The filters themselves also usually aren't determined by what the user said in the prompt, but rather other attributes of the user making the request. For example, consider the newspaper example from before. Say some of your articles are published freely to the open internet, and others can only be accessed by paid subscribers. Each article could have a piece of metadata storing whether it is a free or paid article. When a user searches the database, the system can detect whether they're signed in as a paid subscriber. If not, then a metadata filter would be set to exclude paid articles from search results. Similarly, if your newspaper prints articles in many regions of the world, each article could have a piece of metadata storing the region where the article was published. When a reader queries the system, you can detect in which region they're located and only return articles from their region. Metadata filtering has a number of advantages. Firstly, it's conceptually simple, making it easy to understand how the system works and debug issues. Second, it's a fast, mature, and well-optimized approach. Finally, and perhaps most importantly, it's the only approach that allows your system to decide whether documents are retrieved based on rigid criteria. If you want to strictly define what kinds of documents should or should not be included in a retrieval, metadata filtering is the only approach that can give you that behavior. That said, Metadata filtering has significant limitations. It's not really a search technique, so much as it is a tool for refining the results of the other two techniques you'll see in this module. It's overly rigid, ignores a document's content, and lacks any way of ranking documents once they've passed the filter. While it's very likely that RAG systems you build will include metadata filters of some kind, building a retriever that relied exclusively on metadata filtering would be essentially useless. Metadata filtering is simple and effective, but needs to be paired with other search techniques in order to provide real value. In particular, you'll need a way to determine if a document's contents are actually relevant to your prompt. So join me in the next video to see how keyword search addresses some of these needs. Let's start our exploration of search techniques with keyword search. This technique has powered retrieval in databases and search engines for decades, and yet its simplicity and effectiveness make it a key component of retrieval in modern RAG systems. Let's have a look at how it works and what strengths it brings to your retriever pipeline. Keyword search is a technique that retrieves documents based on whether they share words in common with the prompt. The idea is basically that documents that contain a lot of words from the prompt are more likely to be relevant. Here's how it works. Both the prompt and each document are treated as a bag of words. This means the order of the words is totally ignored, and all that matters is which words are in the text and how often. For example, the text "making pizza without a pizza oven" contains the word pizza twice and the words making, without, a, and oven once. These word counts are stored inside of a vector. The vector has one spot for each word in the system's vocabulary, so there could easily be tens of thousands of spots. Each number in the vector counts how often that word appears in the text. Since most of the locations hold zeros, these are also called sparse vectors. To prepare the knowledge base for retrieval, a sparse vector is generated for each document. All of these vectors can be arranged in a grid, which is referred to as a term document matrix. Each column is a different document, and each row is a different word. This is also sometimes called an inverted index, since it makes it easy to start from a word and find every document that contains it. It's inverted because usually you start from a document and think of which words it contains. But here, you're starting from a word and finding which documents include that word. This inverted index can be created once prior to processing any search. When a prompt is sent to the retriever, a sparse vector is quickly generated for the prompt. Now that each document and the prompt have a sparse vector, you're ready to start scoring and ranking documents. The simplest approach is to just award documents points when they contain words in the prompt. Each word in the prompt is called a keyword. In the example prompt from before, you'd start with the first keyword, making, and find its row in the index. Then you go across that row and award 1 point to every document that contains at least one copy of the keyword. You then complete the same process for every other keyword in the prompt. If a document contains the keyword, it scores a point. This prompt contains 5 keywords, meaning the highest possible score is 5. Once you're done, the total scores can be used to rank documents, and the documents with the highest scores are retrieved. One shortcoming of this simple scoring approach is that it doesn't capture whether a document contains keywords multiple times, which likely indicates greater relevance. A simple fix is to increase a document's score every time it contains a keyword, not just the first. Now, you can find the row of each keyword in the matrix and just award each document the number of points in its column. This introduces a new problem, however, which is that longer documents may contain the keywords many times simply because they're longer. To correct for this, you can divide each document's score by the number of words in that document. This normalized score levels the playing field. It rewards documents in which keywords make up a greater share of the total text and de-emphasizes long documents that might contain keywords many times simply because they're so long. This approach is pretty good, but it awards points for all keywords equally, whether they're filler words like the or less common words like pizza, whose presence is a much better indication of relevance. To correct for this, you can again weight terms, but this time using a measure called inverse document frequency, or IDF. To use this approach, you need to calculate an IDF value for each word in the system's vocabulary. For each word, you'll count how many documents it appears in and then divide by the total number of documents. If your knowledge base has 100 documents and the word pizza appears in 5 of them, it would have a document frequency of 5 over 100, or 0.05. A common word like the might appear in all 100 documents, so this document frequency would be 100 over 100, or just 1. Since you want to reward rare words, you now flip the fraction upside down or invert it. Pizza's IDF would now be 20, while the has an IDF of just 1. At this point, rare words have a significantly higher IDF than common ones, which can overly reward rare words. For this reason, the log of the IDF is what's normally used. Rare words still have a greater weight, but it's less exaggerated than before. The result is an IDF value for each word that captures how rare it is across the knowledge base. To use these values in scoring, first the values in the inverted index are updated, multiplying the numbers in each row by that word's IDF score. The resultant matrix is a term frequency inverse document frequency matrix, or TF-IDF matrix. To score the documents in the knowledge base, you just use the same approach as before. For each keyword in the prompt, go across its row and award each document the TF-IDF score it has in that row. The TF-IDF scores produced by this approach are a standard baseline for the performance of keyword retrieval. The highest scoring documents will frequently use keywords, and in particular, will feature many keywords that are rare across the entire knowledge base. Looking at the earlier prompt, documents containing rare words like pizza or oven will likely score much better than documents that contain common words like or without. While TF-IDF is a foundational approach to keyword search, modern systems tend to use a slightly refined version of this approach called BM25. Join me in the next video to learn how that works and then reflect on the strengths of keyword search and how it fits inside your RAG system. While TF-IDF remains a classic keyword search algorithm, the algorithm used in most retrievers is called Best Matching 25, or more simply BM25. It's called this because it was the 25th variant in a series of scoring functions proposed by its creators. It makes a few improvements upon TF-IDF, so let's explore how those work. Here's the formula for BM25. It actually works very similarly to TF-IDF with a few key additions you'll see momentarily. This formula generates the relevance score for a single keyword for a particular document. Summing these scores up across all keywords generates a total relevance score for a single document, which can then be used for ranking. Let's now see how BM25 improves on TF-IDF. First, documents score diminishing returns as they include more instances of a keyword. The idea here is that a document that includes the keyword pizza 20 times isn't actually twice as relevant as one that includes pizza 10 times. This behavior of discounting additional instances of a keyword is referred to as term frequency saturation. Second, longer documents are still penalized as they are in TF-IDF. But in BM25, these penalties are also diminishing. While penalizing long documents is important, TF-IDF can do so too aggressively in a way that overly discounts longer documents. BM25 applies diminishing additional penalties as documents grow in length. The result is that long documents still score highly as long as they have a fairly high frequency of the keywords. This process of adjusting scores based on document length is called document length normalization. BM25 also differs from TF-IDF in that it includes two tunable hyperparameters. These allow you to control the degree of term frequency saturation and document length normalization, or in other words, how rapidly documents stop being rewarded for repeated keywords and penalized for increased length. In a production retriever, you would tune these hyperparameters in order to land on an overall scoring system that best fits the data in your knowledge base. In a production retriever, the standard keyword search algorithm is BM25. It tends to perform significantly better than TF-IDF at finding relevant documents, is roughly equivalent in terms of the computational resources it requires, and the ability to tune its hyperparameters to your dataset makes it much more flexible. Let's briefly review keyword search and talk about how its strengths are used inside of a typical retriever pipeline. The core idea of keyword search is that you match documents to prompts based on how frequently keywords from the prompt appear in each document. As a part of this process, both prompts and documents are converted to sparse vectors that count how often each word in the system's vocabulary appears in that piece of text. TF-IDF or BM25 are just different approaches for processing these sparse vectors in order to score and then rank documents. These methods also account for important factors like the rarity of a keyword, how often a document contains a keyword, and document length. BM25 is the most commonly used keyword search algorithm that has withstood the test of time for decades since its invention. It strikes a good balance between complexity and performance in real-world applications. The primary strength of keyword search is its simplicity. It's a relatively straightforward approach that works well in practice, often capable of performing quite well on its own and frequently setting a competitive benchmark that more advanced techniques may struggle to surpass. It also ensures that retrieved documents will contain the keywords from your user's prompt, especially in situations when you expect users to use technical terminology or exact product names. This kind of exact keyword matching is particularly important. Despite all its strengths, keyword search does have weaknesses. It ultimately depends on the query containing keywords that exactly match the words in the document. If a user sends a prompt that has a similar meaning to a document, but just doesn't include the right words, keyword search won't be able to find that match. So let's have a look at semantic search and how it addresses this problem. Now let's turn our attention to semantic search. Semantic search is able to match documents to prompts based on shared meaning and can capture nuances that keyword search misses. For example, a keyword search is unable to match the words happy and glad even though they're synonyms, and would incorrectly match Python, the programming language, and Python, the snake. The technology underlying semantic search is quite remarkable, so let's dive in to see how it works. On a very high level, semantic search works just like keyword search. Every document is mapped to a vector, and so is a prompt. Then, the prompt vectors and document vectors are compared to generate scores and find the documents that most closely match the prompt. The primary difference is the way vectors are assigned to each document and prompt. In keyword search, you just count how often each word appears in the piece of text. In semantic search, however, you generate vectors by running the document or prompt through a special mathematical model called an embedding model. Embedding models map words to a location in space. This location is represented by a vector. For example, the embedding model might map the word pizza to the vector 3, 1, and the word bear to the vector 5, 2. In 2 dimensions, you could represent these as points on the XY axis. Now here comes the part that almost feels like magic. The embedding model will map semantically similar words to nearby locations in space. For example, the word food and cuisine would get embedded closer to one another, and the words trombone and cat would be embedded further apart. Similar meanings lead to similar positions. The X and Y axes here don't have any simple interpretation. There's no food axis and animal axis here, or at least not one that's easy to see. Instead, you should just think about points floating around on the 2D plane, with similar meaning words clustered together. Words have many complex relationships, and creating sensible clusters in 2 dimensions probably won't work. If the vectors each had 3 components, you can imagine embedding them into 3-dimensional space. Now there's more room where clusters of related concepts can form, and to capture nuanced relationships between them. In most embedding models, however, these vectors have hundreds or even thousands of components, giving an incredible amount of flexibility on where to embed each point. It's impossible to graph or maybe even imagine this high-dimensional space, but mathematically, all the same principles hold. The vectors give the coordinates of locations in that space. Similar concepts are embedded close together, and dissimilar concepts are embedded farther apart. Even though this example is focused on individual words, embedding models exist for many kinds of input data. There are embedding models for individual words, sentences, and even entire documents. These models take different kinds of inputs, but in each case, output a single vector that specifies a point in space. Just as with single words, if the vectors are closer together, the pieces of text have similar meaning. Consider 3 sentences. He spoke softly in class. He whispered quietly during class. Her daughter brightened the gloomy day. When projected into vector space, the vectors for the first 2 sentences will be closer together, while the third sentence would be far away from the other 2. In order to quantify the similarity of different pieces of text, you can measure the distance between their vectors. There's a few ways to do this. For example, the Euclidean distance, you might remember from geometry class, just measures how far apart 2 vectors are by drawing a straight line from one vector to the other, the shortest possible distance between them. The formula to calculate this is essentially the Pythagorean theorem, but scaled up across more dimensions. In very high dimensional space, however, every point tends to be pretty far away from every other point. A much more commonly used measure of distance is cosine similarity, which measures the similarity in the direction of 2 vectors, regardless of whether they're that close to one another in space. The vector 10, 10 and 100, 100 aren't that close to one another, but they face in the same direction. Cosine similarities range from 1, when the vectors face exactly the same direction, to -1, when they face exactly the opposite from one another. You will also occasionally see the dot product, which measures the length of the projection of one vector onto another. If 2 vectors are similar in length and direction, the projection will be larger. If they're at a 90-degree angle, the projection length will be 0. If they're facing opposite directions, the dot product will be negative. If math's not your forte, don't worry. You'll likely never need to implement these distance measures, but knowing how they work is helpful. For example, for both the dot product and cosine similarity, higher values reflect closer vectors, which ultimately reflects more similar concepts. Cosine similarity ranges from -1 to 1, and the dot product can take any value between negative and positive infinity. Let's see how this distance measure is used to power semantic search. First, all the documents are projected into vector space by the embedding model. Thanks to how the embedding model is designed, documents with similar meaning will be closer together, and documents with dissimilar meaning will be farther apart. Next, you embed the prompt to get a vector of its own. Now, you can measure the distance between the prompt vector and the vector of each document. Thanks to the way the embedding model is designed, whichever documents are closest will also have the most similar meaning. At this point, ranking documents is easy. You just sort documents by their distance from the prompt and return the documents which have the shortest distance. Thanks to the way the embedding model works, you've just found the documents with the most similar meaning to your prompt. Semantic search is fairly straightforward if you take for granted that the embedding model works properly. Similar concepts end up mapped to nearby locations. And so you can quantify relevance by the distance between vectors. Digging a little deeper into how embedding models are trained and how they almost magically know how to place similar concepts closer together can help deepen your understanding of semantic search in general. So join me in the next video to dive a little deeper on this key component to semantic search. That's the end of our tour of the different search and filtering techniques used inside of a retriever. So let's have a look at how they can be used together as part of a hybrid search technique to take advantage of their different strengths. To start, let's review how each technique operates and its key benefits. Metadata filtering uses rigid criteria stored in document metadata to narrow down search results. It's fast, easy to implement, and easy to interpret. It may not be a great search technique on its own, but it provides a strict yes-no filter that neither of the other approaches can provide. Keyword search scores and ranks documents based on having the same keywords found in the prompt. Keyword search is still quite fast and easy to implement, and it can even do an excellent job at finding relevant documents. It performs particularly well in instances where prompts and documents contain technical keywords or product names, as results will contain those exact words. Keyword search relies on exact matches, however, and so is unable to retrieve documents with similar meanings but different words. Semantic search scores and ranks documents based on having similar meaning to the prompt. Documents and prompts are embedded as vectors whose location in space captures their meaning. Finding the most similar documents to a prompt just means you need to find the documents whose vector embedding is closest to the prompt's vector. Semantic search is slower and more computationally intensive than keyword search, but it provides a flexibility that no other search technique can. With all three approaches having relative strengths, here's how they're typically combined into a hybrid search pipeline. First, as always, a prompt is received by the retriever. The retriever then performs both a keyword search and a semantic search using that prompt. The result are two ranked lists of documents, one that was scored and ranked using keyword search, and another using semantic search. If you like, imagine each search technique returning 50 documents, with many documents appearing in both rankings, but perhaps in different order. Next, both of these lists are filtered using a metadata filter to remove documents that are irrelevant. For example, the filter might remove documents that aren't relevant to their work. In this example, the keyword search list is left with 35 documents, and the semantic search only 30. Now, these two ranked lists need to be combined to form a single ranking. A commonly used algorithm for combining these rankings is called reciprocal rank fusion. This algorithm rewards documents for being ranked highly on either list, while allowing you to control whether to give more weight to the keyword or semantic ranking. Here's the formula for reciprocal rank fusion. Documents score points based on their ranking in each list. K is a hyperparameter, but for now, pretend it's 0. In that case, each document scores points equal to the reciprocal of their ranking. So first place scores 1 point, second place scores a half a point, and so on. Documents acquire points from each ranked list, and their total scores are used to calculate a final ranking. In the case of your retriever, that's just two rankings, their keyword rank and semantic rank. If a document appeared second in one list and 10th in another, it would score 1/2 or half a point from the first ranking and 1/10 or 0.1 points from the second, for a total score of 0.6. These scores are then used to re-rank all the documents. Let's go back to that K parameter. K is used to control the impact of the highest ranked documents. When K is 0, the top ranked document in any list will instantly shoot to the top of the overall ranking, even if it's only highly ranked once. For example, the top ranked document scores 1 point, and the 10th ranked document scores 1/10. That's a 10x difference. Increasing k to something like 50 balances things out. Now, the top ranked document scores 1/50 points, and the 10th ranked document scores 1/60, which is a much more modest difference in scores. It still pays to be ranked first, but not to such a degree that it dominates rankings on any other list. Notice that RRF only cares about the rank of the document in each list, not the scores that led to those rankings. Even if the top ranked document scored considerably better than the second, that information is not considered. Inside a retriever, hybrid search typically has a second hyperparameter called beta, which allows you to weight the rankings produced by either the semantic or keyword search. For example, you could set beta to 0.8, assigning 80% of the importance or weight to the ranking provided by semantic search, and only 20% to the ranking provided by keyword search. A 70-30 split, 70% semantic, 30% keyword search, is typically a good starting point, and you can tune this for your particular system to see what works best. For applications where exact word matching is really important, but you want some semantic similarity, you'll want to weight keyword search results more heavily than semantic search results. In other cases where semantic similarity is more important and keywords are less crucial, you'll want to weight vector search results more heavily than keyword search results. At this point, your retriever is actually ready to return its results. Depending on how many documents were originally requested, usually referred to as top K, the most similar K documents from this final hybrid ranking are returned by the retriever. Hybrid search allows a retriever to take advantage of the different benefits that keyword search, semantic search, and metadata filtering provide. Keyword search provides exact word matching. Semantic search allows for fuzzier matching based on meaning, and metadata filtering filters documents out using strict criteria. There's also ample opportunity to change how this hybrid system works, whether it's adjusting the parameters of the BM25 algorithm, choosing which metadata to filter on, or changing the weighting of keyword versus semantic search in the reciprocal rank fusion step. This hybrid approach lets you play to each approach's strengths and tune the system's performance to the data in your knowledge base or the needs of your overall project. To do that tuning, however, you need a way to measure how well a retriever is performing. So join me in the next video to look at how retrievers are evaluated. Just like any piece of software, once your retriever is up and running, you'll want to know if it's actually working. While you can evaluate a retriever in terms of latency, throughput, resource usage, and so forth, what ultimately matters is search quality. In other words, is it finding relevant documents? Let's look at a few ways you can answer that question. There's a few ingredients common to most retriever quality metrics. First, you'll need the prompt itself, as retrievers may perform well on one prompt and poorly on another. Second, you need the ranked list of documents the retriever returns from that prompt. And finally, you need a ground truth list of all the relevant documents in your knowledge base that the retriever should return. In other words, if you want to grade your retriever, you need to know the correct answers. Two of the most common retriever quality metrics are precision and recall. Precision is calculated by dividing the number of relevant retrieved documents by the total number of documents retrieved. Recall, on the other hand, is calculated by dividing the number of relevant documents retrieved by the total number of relevant documents in the knowledge base. Here's an example to help you understand the difference. Suppose you know that your knowledge base has 10 documents relevant to a prompt because you hand mark them. You run your retriever on the prompt and it returns 12 documents, 8 of which are relevant. The precision is 66% since 8 of the 12 are relevant, and the recall is 80% since 8 of the 10 relevant documents were retrieved. Now, you adjust your retriever settings and run the prompt through it again. On this second run, it returns 15 documents, 9 of which are relevant. Your retriever returned 3 more documents than last time, but only 1 more relevant document. Precision drops to 60%, or 9 out of 15. Recall, however, increases to 90%, as you found 9 of the 10 relevant documents this time. In other words, you've traded a little bit of precision away to get a bit more recall. Precision penalizes a retriever for returning irrelevant documents and can be thought of as capturing how trustworthy the results are. Recall penalizes a retriever for leaving out any relevant documents and measures how comprehensive the retriever is. The only way to have perfect recall and precision is to rank the relevant documents most highly and only return those documents. Otherwise, you're often trading off between the two. Retrieval metrics are influenced by how many documents the retriever returns. So to standardize, they're usually talked about in terms of the top K documents, meaning the K documents that the retriever ranked most highly. For example, consider this ranked list of documents returned by a retriever. The precision at 5 in this example is 40%, since only 2 of the top 5 documents are relevant. The precision at 10, meanwhile, rises to 60%, as 6 of the top 10 documents are relevant. Suppose there are 8 relevant documents in the knowledge base. The recall at 10 here would be 6 out of 8, or 75%. Depending on which value of top K you choose, you can quickly produce new precision and recall values. Top 5, top 2, or top 1 metrics can be used when stricter standards are important. Often, though, a slightly more generous range between top 5 and top 15 is used. To give a more holistic view of retriever performance, mean average precision, or MAP at K, evaluates the average precision for relevant documents in the first K documents retrieved. First, let's calculate a related metric called average precision at 6 for this example. You list out the 6 documents the retriever ranked most highly and calculate precision at K for every row. Next, you add up the precisions only for rows that contain relevant documents. Here, those rows are 1, 4, and 5. So you add 1, 0.5, and 0.6. Finally, you divide by the number of relevant documents retrieved in the top K, which in this case is 3. That gives us an average precision of 0.7. To calculate mean average precision, you just calculate average precision across many prompts and sets of documents retrieved, and average those values. This just tells you what the average precision would be for a typical prompt your retriever receives. MAP rewards ranking relevant documents highly. If an irrelevant document sneaks into a spot high up in the rankings, it'll decrease the precision at the rank of every relevant document below it, bringing down the overall average. A high MAP value is therefore a good indication that a retriever is placing the relevant documents it finds high up in the ranking. A final common metric is reciprocal rank, which measures the rank of the first relevant object in a returned list. For example, if the first relevant object appears at rank 2, the reciprocal rank would be 1 over 2, or 0.5. If it were at rank 4, the reciprocal rank would be 0.25. The further down the list the first relevant document appears, the worse the reciprocal rank. This is typically performed over multiple prompts to get the mean reciprocal rank, or MRR. MRR reflects how soon, on average, you can find a relevant item in the retriever's ranking, and emphasizes the importance of including at least one relevant document as high in the ranking as possible. For example, if you complete 4 searches using a retriever, and the first relevant document in each ranking appeared in the first, third, 6th, and 2nd spot in the ranking, you'd calculate the mean reciprocal rank by dividing 1 by each of those numbers. You then average those values. Here, that gives you 1, 1/3, 1/6, and 1/2. Adding those values and dividing by 4 gives you the mean reciprocal rank of 0.5. With many metrics available, it's important to know how best to use them together. Recall, or recall at K, is the most foundational and most cited metric for retrievers because it captures the most fundamental goal of the retriever, finding relevant documents. Precision and map build upon this by assessing whether the retriever is including many irrelevant documents or how effectively the retriever is ranking them. Mean reciprocal rank is a bit more specialized, but helps identify how well your model performs at the very top end of its ranking. These metrics can both help evaluate the performance of your retriever and help you decide if adjustments you make to a system are working. For example, you could adjust how heavily you weight semantic or keyword search in your hybrid retrieval system and then see what effect that has on your retriever's recall or precision for a collection of sample prompts. If there's a downside to these metrics, it's just that they all depend on having ground truth, relevant documents for a collection of sample prompts. This can be a time-consuming and manual process to compile. The end result, however, is a system you can monitor during both development and once it's in production. Okay, you've covered all the most important concepts underlying a retriever in a typical RAG system. Join me in the next video and let's summarize the main takeaways from this module.